Welcome to the physics class, BSc, 3rd semester, paper 9, Geometrical and Physical Optics, Electricity 1 and Basic Electronics. In this paper, Unit 3rd, Theory of Dielectrics and Moving Coil Galvanometer. In the session 10, we learnt dielectric constant and its experimental determination. Now we see what is dielectric constant. Already this learned in the first class. Dielectric constant is a known relative permittivity, is also known as a relative permittivity. Epsilon or its symbol, or in some textbook K is also in its representation. So it's measure the of a material ability to storing the electrical energy in an electric field. It compares how much electric field is reduced inside of the material compared in a vacuum. So it is symbolically represented as an epsilon r is equal to epsilon dividing by epsilon naught. Epsilon is the permittivity of the dielectric material. Epsilon naught is the permittivity in free space or vacuum, and its value approximately equals to 8.854 into 10 power minus 12 per meter. Sum of the dielectric constant for the sum of the materials is in here as in vacuum as in nearly 1 dielectric constant. Here is very close to 1, that is approximately equal to 1.0006. Water has a high dielectric constant, that is approximately equals to 80 at room temperature, which is why it is a good dissolving salts. Like materials like glass, mica, ceramics have higher values of the useful capacitor. So what is meant by capacitance? The capacitance of a capacitor will be increases higher dielectric constant. Capacitor, it is a storing of the electrical charges. The capacitance of the capacitance increases, it means it has a high dielectric constant. It is represented by C is equal to epsilon r into epsilon naught into A dividing by D. A is the area of the plate, C is the capacitance, and D is the distance between that plates. Next, we will determination of the dielectric constant of a solid by Hopkinson's null method. So the experimental arrangement of this Hopkinson null method is as shown in the diagram. So first we see in the construction setup. It has a quadrant electrometer needle of the potential V, that is quadrant electrometer's needle potential. Here C1 has a variable capacitor, here C1 has a variable capacitor, and C2 has a God ring capacitor, and C2 has a God ring capacitor, movable earth with a plate, and whose movement is measured in a micrometer screw M. Second capacitor, it will be measured in a micrometer screw M, and battery is a midpoint and is earthed, and battery B is a midpoint and it can be grounded. Battery is earthed, and providing a potential minus V and the plus V at the ends. Providing a potential minus V and the plus V at the ends. Next, charging is when capacitor C1 and C2 are charged to equal and opposite potential. Pressing the plug key K. Pressing the plug key K is used for charging for the capacitor, and measurement is releasing in the plug key K. The capacitors charges the quadrant electrometer. The capacitor will be charges at the quadrant of the electrometer. Null condition is by adjusting the using C1 to equalize the capacitance C1, and C2 has in charging become equal, charges become equal, resulting in the zero deflection of the electrometer, Hence it is called as a null method. Null method. So what is the working principle? So initial balance condition, the capacitor of the C1 is adjusted until there is no deflection of the quadrant of the electrometer, When key is pressed and released, this significant capacitance C1 is then balanced against the initial capacitance of the C2. So C1 is an here C1 is a variable capacitor and C2 is a constant. So C1 will be varied until we get in the null detection in case of the electrical quadrant. Next, introducing the dielectric material. When dielectric slab of the thickness T and dielectric constant epsilon is introduced between the plates of the C2, that increases the capacitance of the C2. It means in this case of the C2 will be introducing the dielectric slab, the capacitance of the dielectric which will be increases, means capacitor 2 having a large number of storing the charges. Next, re-establishment the balance. So the lower plate of the C2 is moved downward by a distance x by micrometer screw until the electrometer again shows the null deflection. This means new capacitance C2 will be now equal to the C1. So again it will be C1, C2 it can be moving to the distance d until the null deflection will be obtained into the electrometer. Capacitance equals to C1. Next measurement, the distance x is measured through the lower plate of the C2 has moved. Measure the micrometer screw. Distance is crucial and calculating the dielectric constant. Formulaic relationship, let A be the effective area of the guard of the capacitor and D is the initial distance between them. The change in capacitance due to the dielectric and subsequent movement of the plate allows for the calculation. Epsilon r is based on the measured distance x and the thickness T of the dielectric slab and the N area A. So then C2 is an capacitor without dielectric is C is equal to epsilon naught A into A dividing by D. C2 with dielectric, second condition, epsilon naught A dividing by D plus x minus T plus T dividing by epsilon R. The capacitance of the two cases in the same. Therefore, these two equations will be equating. We will get epsilon A dividing by D, which is equals to epsilon A dividing by D plus x minus T plus T by epsilon R. Here epsilon naught A, epsilon naught A get cancelled. Therefore, D is equals to D plus x minus T plus T by epsilon R. D and D gets cancelled. We will getting epsilon R is equals to T dividing by T minus x. Hence the dielectric constant of the material of the slab will be calculating formula. This is the method of dielectric constant of a solid by Hopkinson's null method. Now we see the determination of dielectric constant of a liquid Hopkinson method. So construction of the diagram is as shown in the diagram. So now we see the determination of dielectric constant of a liquid Hopkinson method construction. In this construction diagram, capacitor will be set up. This method using a sliding capacitor C1. C1 it has a sliding means rolling like a capacitor and a special cylindrical capacitor C2. C2 has a special type of cylindrical capacitor. C2 consists of a double cylinder A and B. There are two cylinders will be insulated metallic cylinder C. Insulated metallic cylinder C hung inside. The circuit arrangement. The cylinder C has connected to an K2. The cylinder C has connected to an K2 and midpoint of the battery is earthed. The midpoint of the battery is going to earthed or ground. The initial adjustment of the air with an air is a dielectric capacitor AB. First medium we have to use it as an air as an dielectric. And this sliding capacitor C1 is adjusted until there is no deflection in the electrometer. So So sliding capacitor will be C1 will be adjusted until there is no deflection will be obtained into the electrometer. When the keys K1 and K2 are pressed and released. Next, length measurement is the L1 is the inner side of the sliding cylinder C. Inner side of the length of the cylinder C is recorded at this point. Capacitance equality. Capacitance equality at this stage. Capacitance of the AB with air is equal. Capacitance of the AB with an air is equal to the capacitance of the C1. Capacitance of the air will be equal to first capacitor C1. So with working in an air, capacitance in an air, capacitance of the capacitor AB with filled with an air is given by C of air, which is a formula 4 pi epsilon naught L1 dividing by 2 log E log to the base E into B by A. Here L1 is the initial length of the sliding cylinder. A and B are the radii of the inner and outer cylinder of the capacitor 1. Next, capacitance in liquid. In the capacitance space between A and B filled with an experimental liquid, the capacitance C1 is readjusted until there is no deflection will be obtained in the micrometer, indicating the same capacitance. A new length L2 of the sliding cylinder is be noted. Capacitance of the capacitor AB with filled with a liquid is given by C of liquid is equal to 4 pi epsilon naught L2 dividing by 2 log to the base E. B by A is the formula. Next, dielectric constant will be measured. The dielectric constant of the given liquid is the ratio of capacitance of the liquid to the capacitance within air, which simplifies the ratio of the length epsilon r is equal to capacitance of the liquid to the capacitance of the air. We will getting these two equations we can divide. We will getting the L2 by L1 is the formula. For knowing the measurement of the lengths L1 and L2, we will measuring the dielectric constant of that given liquid. This is the method of Hopkinson method for determination of the dielectric constant. Now we see what are the applications of the dielectrics. So capacitance, first application is the capacitors. Dielectrics are used in insulating materials between the plates of the capacitors because they increase in the capacitance by reducing electric field inside of the capacitor. Next, insulation in an electrical device used in cables, transformers, motors and generators to prevent unwanted current flow. Common dielectric materials like mica, glass, ceramics, rubber, plastic, etc. Radio and TV broadcasting phenomenon. Dielectrics are used in the tuning circuits and antennas to control the frequency. Dielectric heating method. In microwave ovens and industrial heating, dielectric materials are heat up when the exposed to heat frequency of the electromagnetic fields. Next, electro-optical phenomenon or applications. In this case, materials like in liquid crystals and electro-optical crystals and dielectrics are used in an LCD displays and optical modulators. Storage devices used in a non-volatile memory devices like DRAM due to their ability to store the electrical charges. And dielectrics are also used in high voltage applications, that is high voltage capacitors and circuit breakers withstand high electric fields without break-in. Measuring instruments like ballistic galvanometer, dielectrics are used for the capacitance of the measurement. Now we see the certain applications in the dielectric capacitors. In transportation field, electromagnetic ejection, electric vehicles, renewable energy sources, micro weapons, electronic and electrical systems. and also see the certain fields in the applications, variables, implantable devices, energy and harvesting, communications and portable devices in smart cities, etc. Thanks for watching this video.